Hi, my name is Anna Prony. Today we're going to be solving this problem that's given in the statement. So we have for the beam system shown below, find the principal stresses and max shear stress at point H. So that's going to be down here. All three sections are solid cylinders with a diameter of 5 centimeters. So in order to find the principal stresses, the max shear stress, specifically at point H, what we need to do first is actually figure out the reaction forces and reaction moments that are occurring at the cut plane of point H. So if I go ahead and say this is the cut plane, right? That's the cut plane. If we figure out all of the reaction forces and the moments that occur there, we can then look at how each one creates a stress at that point. So in order to find the reaction forces and reaction moments, I'm going to go ahead and draw a free body diagram. Luckily, I have a cool tool here that's going to kind of assist me with that because I am a poor artist at best. So we have our kind of cylinder system here, and we have this like longer pipe coming out this way, and the shorter pipe coming out at the top. Whoops. I'm going to go ahead and go back to freehand. So here's your long pipe, short pipe, top pipe. And this is the cut plane, so this is point H. This is the point we're concerned about, point H. And we have a bunch of these forces here. So we have a force that's coming down, straight down, that's going to be 13 kilonewtons. And a force that's coming straight to the right, which is going to be 9 kilonewtons. And we have a force that's coming straight down here, that's going to be 17 kilonewtons. And a force that's coming straight down in the longitudinal direction of this pipe, 50 kilonewtons. And I believe those are our only four forces. Dimensionally, this is going to be 2.5 meters away from the axis of the main cylinder. This is going to be 1.5 meters. And this is going to be, we'll say 4 meters off the ground for the first pipe. And the second one is going to be 6 meters off the ground for the second pipe, 1.5 meter pipe. Now that we got that all figured out, what are our reaction forces and reaction moments going to look like? Well, we can go ahead and draw a quick kind of almost coordinate system type thing here. This is going to be our reaction in the y direction. So we'll label this as RY. They've already labeled, as you can see, these directions as Z and X. So I'm just saying that's our third direction. We're just going to say that's Y. So the reaction force is going to be going up. It's going to be called RY. The moment that rotates about that reaction force is going to be the moment of Y, MY. Since we already are told this direction, that's going to be Z, so that the whatever reaction force that is going in that direction is going to be reaction Z, and whatever moment that rotates about is going to be the moment Z. And then lastly, Rx and Mx. And those are going to be our reaction forces, and they're taking place right at this cut plane here. I did draw it a little further down just so you could see it clearly, but this origin point is going to be right at the origin point of the cut plane of this kind of like cylinder here. Okay, so now that we have that, all we got to do is kind of solve this like it's a statics problem. So all we have to do is find the force and moment at this cut plane that is created by each of these forces. So to do that, I'm going to set this up. I'm going to say, okay, I want my position vector here, and I want my force vector here, and I want my moment vector, or just my moment vector here. And this is going to be I, J, K, I, J, K, I, J, K. And we're going to do this for each and every force that exists in this system. So we'll start off, and we have 4 forces here, right? We have the 9, 13, or I said that backwards, 9 and 13, 17 and 50. So we'll just choose one and get started. Let's start with the 9 kilonewton force. So I'm going to say Y9 kilonewton force is over here. Its position vector is the distance away it is from the cut plane. So what is the distance strictly in the y direction that this force acting right here is away from my cut plane, which is right here? Well, in the y direction, it's going to be 4 meters, right? So J is our y direction, so we'll go ahead and put that down, right? This is x, and this is y, and this is k. Z, right? So what about in our x direction / I direction? Well, it's 2.5 meters away from our cut plane, so that's in the z direction, and in our x direction it's 0. So in our x direction it's going to be 0. In our k direction it's going to be 2.5 meters away. So that is our position vector. So we say, okay, our force vector is going to be dictated by where the force is pointing. So since it's acting on this point, and it's pointing this way, it's pointing strictly in the x direction and not in any other direction. So we're going to have 0 and 0 for j and k. And the magnitude of the vector for the x direction, which is going to be 9 kilonewtons. So we'll say 9. And to find the moment vector of these two, all we have to do is take the cross product of your position and force vector, which hopefully we kind of remember how to do. I like going through the monotonous steps because I tend to make mistakes with this kind of step in the problem. So I'm going to go ahead and set it up where you have ijk. Here's our position vector that goes first in line, and our force vector goes second. So then we're going to kind of figure this out. So figuring out what the magnitude of our I hat direction is, we look at the square that is not under the I, and we say, okay, the multiplication of this diagonal minus the multiplication of this diagonal is equal to the magnitude of the I position in our moment. So that's actually going to be 0 minus 0, right? 0 minus 0 I hat minus j, so it's going to be this square. So we say, okay, 0, 0, that's the first diagonal, minus 9 times 2.5. So here I'm going to actually say 9 times 2.5 is equal to 22.5. And that's going to be j. Plus, now, keep in mind, the 9 kilonewtons is going in the direction of my x, so this is a positive 9 kilonewtons. As is the position vector, so this is going to be a positive. It's going up in the y direction and up in the z direction. So all of our numbers are positive here. And lastly, for the k, we're looking at this box. So we say this diagonal, which is 0, multiplied by, minus the multiplication of that diagonal, which is going to be 9 times 4, which is 36. Minus 36. And that's going to be k hat. And we can just go ahead and put those numbers up. So that's going to be negative times a negative is positive 22.5 in the j hat direction. And in the k hat, we have negative 36. Okay, perfect. So that's for our 9 kilonewton force. This is 0. Let's go ahead and move on to the next force, and hopefully this next one will go faster. So we'll say, okay, let's do the 13 kilonewton force. And since it's acting on the same point, we can go ahead and copy our position vector. So we say, okay, for the 13 kilonewton force, it's the same position vector. In terms of the force vector and where it's pointing straight down, so that's going to be a negative j direction. And for the magnitude of it, we'll just say it's going to be at 13, get 0 on the other two. And the moment, we just take the cross product again. So I'm going to go ahead and go through that process. Make sure I'm not skipping any steps here. And we'll say, here's our position vector. That's going to be 0, 4, 2.5. Here's our force vector, 0, negative 13, 0. I is going to be 0 minus a negative 13 times 2.5. So we'll say 0 minus, that's going to be 13 negative times 2.5, negative 32.5. I minus j, which is going to be 0 minus 0. So that's 0j plus, and then k, that's going to be here 0, and then also 0. That's going to be 0k. So we have a positive 32.5 in the I direction for our moment, and zeros here and here. Okay, perfect. Okay. So that's 2 forces out of our 4 forces down, so halfway done. Let's do our 17 kilonewton force now. So we'll say, okay, for our 17 kilonewton force, our position vector is what? Well, it's going to be 6 meters up in the positive j direction and 1.5 meters in the positive x direction. So that's going to be 1.5, this is going to be 6, and this is going to be 0. And in terms of the force vector, it's pointing straight down, so that's going to be a negative 17. And our force vector, and we'll take the cross product of those two. We say, okay, 1.5, 6, 0, 0, negative 17, 0. And we'll say, okay, first off we have I, so that's going to be 0 minus 0, so 0 I minus j, which is going to be 0 minus 0, which is 0 j, plus k, which is going to be negative 17 times 1.5, and 17 negative, equal to negative 25.5, minus, sorry, here, 0, and that's k. So that's going to be a negative 25.5 in our k hat direction, and 0 everywhere else. Coolio. There's probably a more efficient way to do this than erasing it every time, but I don't know. I'm almost done with this, so we'll just stick with it till the end here. Okay. Lastly but not leastly, we have our 50 kilonewton force, which is acting straight down. Our position vector is just going to be just the j direction, and it is going to be just a positive 6. Our ijk here is going to be, for our force vector, it's just going straight down, so it's going to be negative 50, 0, 0 in the other directions. If we take, we can kind of already see that the moment is going to be 0 because it's kind of pointing on straight down on the axis that it exists on. But we can go ahead and take the cross product and prove that. So that's going to be 0, 6, 0, that's going to be 0, negative 50, 0, and we can say, okay, the cross product for I is going to be 0 times 0, the cross product for j is going to be 0 minus 0, and the cross product for k is going to be 0 minus 0, and that means that we're going to have 0 for our moment there. Okay, so now that we have all that done, and we can go ahead and figure out what our reaction forces and reaction moments are going to be. So we need to find reaction at x, reaction at y, and reaction at z. And the moment reaction at x, and the moment reaction at y, and the moment reaction at z. So how do we do that? Well, these are the forces that are acting at the cut plane, so our reaction force is just going to be equal and opposite to that. So in the x direction, these are all the forces that are acting in the x direction. We need a force that's equal and opposite to it, so that's going to be negative 9 kilonewtons. For our x, what about the y? Well, we got to add all these up. So that's going to be negative 13 plus negative 17 plus 50. So that's going to be 80. So specifically negative 80, and as our total here, and we need one that's opposite and equal to that, so that's going to be a positive 80 kilonewtons for our x, and then we have actually no forces in our z direction, so we have no forces in the reaction z direction. So, and then for our moments here, equal and opposite again. So since this is a positive 32.5, we're going to have a negative 32.5 in our x direction. This is a positive 22.5, we're going to have a negative 22.5 in our y direction. And then we have to add these two together. So that's going to be a 25.5 negative plus 36 negative, and that's going to give you a total z moment, z reaction moment of a positive 61.5. And this is all going to be actually in kilonewton meters. Kilonewton meters. Alright, so now that we've solved for the reaction forces and reaction moments at the cut plane, we can now figure out what stresses they put specifically at that point at that cut plane. And to do that, we'll just go through one by one and check out how each reaction force / reaction moment kind of affects the stress at that point. So let's start with Rx. So we can go up to the very top and we can say Rx is acting in this direction, right? Which means that it's acting in a lateral direction. So this is the longitudinal direction of our cut plane, right? It's going to be, you can think of it as just like the long axis. It's the long axis of our pipe here. So in any direction that is not directly along this axis is going to be lateral, and this is a lateral force. It's not a lateral moment, so we know that this is going to go ahead and be a transverse shear force. Transverse shear force, which means that we're not going to have any normal forces, normal stresses that are created by this reaction force, but we will have a shear stress that is created by this reaction force. And the equation for the shear stress we're going to use in order to find it is going to just be VQ divided by IT. And we'll get into what each of those variables mean in just a hot second. So first off, though, I kind of want to draw a quick diagram. So when we're trying to view exactly how this shear stress, this reaction force here, is affecting at point H, we're going to go ahead and draw the view of the force where it's not acting. So since it's acting along the x direction here, and we want to see the arrow, I'm going to look at it from the yx plane, and we'll go ahead and draw that. So we'll say, okay, kind of a 2D drawing here, changing from 2D, right, from 3D to 2D. This is your y, this is your x, and the pipe that is around it, again, this is 2D, so it's just a square. When we draw it in a 2D, this is the pipe, this is the cutoff of the pipe. Obviously it extends further than this cutoff. It's a bad pipe cutoff drawing, but there you go, you get the gist. And our reaction force, Rx, is negative, so it's acting in the opposite direction that our x direction is acting in, so it's going that way. Hold on, I can draw that better. That's our Rx, and that's going to be a value of 9 kilonewtons. Okay, so now that we have this drawing, where's point H on this drawing? Where's point H? Well, it's kind of directly on the z-axis, meaning that if we look at it from the y-x plane, it's going to be right along dead center on this point here. That's point H, yeah? That's point H. So we have to figure out how this stress, or sorry, how this force, puts how much stress directly on that point. So I'm actually going to go ahead and draw another drawing of this, the bottom view. So if we take this and we kind of flip it so we can see the bottom view. Oof, that's an awful circle. Okay, there we go. And we can see the bottom view. This is going to be our x, right? And this is going to be the z. Okay. It's kind of the z direction, right? You'd have to be looking at it that way. And h is going to be at the very top of the z. So h is going to be here. Remember, our force is acting upon in the x direction. So it's acting this way along with our axis here. Which means that our neutral axis is going to be perpendicular to it. Our neutral axis is going to be directly perpendicular to it. This is our neutral axis. It's also the z-axis. Because if you think about it, if you're pushing a stress, on the circle, it's going to kind of collapse upon the angle that is perpendicular to it. Okay. So, and that's point H. So let's go through one by one and figure out what each of these variables mean with respect to everything that's going on in these pictures here. V is pretty easy to figure out. That's just our shear force. It's plainly given by our reaction force, so that's just going to be a negative 9 kilonewtons. Q is defined as the first moment of the outward area. Okay, and the first moment of the outward area can be found by this equation, where AI is going to actually be your outward area, and YI is the distance of the outward area from the neutral axis. So for this guy, this is our point of interest. This is our neutral axis. So the outward area is the area that is like outside, opposite from the point of interest, meaning that this is going to be your outward area, right? That's going to be your outward area. If the point were here, right, then this would be our outward area. So that's our outward area, and so we can find the outward area by strictly saying, okay, that's going to be 1/2 pi r squared. That's just half of a circle. What's y bar here? Well, it's the distance from the neutral axis to the centroid of this area. So the centroid is going to be somewhere right here. If you want to find the equation for the centroid of a half circle, you can actually go ahead and just look it up in your Mechanics and Materials textbook. It's in the very back. I actually forgot it, so I'm going to do that right now. So this is the Mechanics and Material textbook. In the very back, we have the centroid for a half circle, and it is given by 4r 3 pi, and that's going to be the distance that we're looking for. So Q can be rewritten as 4r divided by 3 pi multiplied by 1/2 pi r squared. And r here, we say, okay, well, what's r? Well, the diameter, we are actually given the diameter of the cylinder in the beginning problem statement. So we're going to go and say that since the diameter is 5 centimeters, as in the diameter is 0.05 meters, the radius is just going to be equal to 0.025. So we can go ahead and plug that into this formula. So 0.025 divided by 3 pi multiplied by 1/2 pi r squared. Whoops, pi 0.25 squared, 0.25 squared. And I'll go ahead and plug that in my calculator, and that should give us a definitive answer for our first moment of the outer area. So So I'm going to go ahead and plug that in. And I might have done something wrong, so I'm going to go ahead and do that again. 4 times 0.025. Okay, and so that gives us a Q value of 0.0000100417. And this is actually going to go ahead and be in meters cubed. And so that's our Q value. What else do we need to find in this equation? Well, we need to check out what I is. I is just going to be your moment of inertia for the shape of your cut plane, which is just a circle. So the moment of inertia for a circle is strictly defined as 1/4 pi r to the 4th. Of course, if you don't know that, you can look it up in the back of your mechanics of material textbook. It's right here where you say, okay, check out, I'm looking for moments of inertia of common geometric shapes. Check out the circle one, specifically the I one. It's given by 1/4 pi r to the 4th. So that can easily be found as well. We just plug in 0.025 for r, which I'm going to go ahead and do, times pi, and divided by 4 is going to give me an I of 0.000000307. Okay. And that's going to be in meters to the 4th. 1, 2, 3, 3. Okay. Yeah. That's your number for I. Okay. And lastly, we're looking at the thickness of the geometric shape at the point of interest. So that is actually just going to be, since this is here and we're looking at the thickness in terms of parallel to the neutral axis, that's just going to be the diameter. So T is just going to be equal to 0.05 meters. And we'll go ahead and we'll plug all those values in to our original equation of VQ divided by IT. So we're going to say tau. Now, to figure out where the shear stress is acting upon, what we're going to need to do is say, okay, what plane is this shear stress acting upon? Well, we already kind of decided that, right? With this picture, we say, okay, this is the plane, the XY plane that the shear stress is acting upon, because here we can see where the stress is acting upon. So, and it's actually, since it's acting in the X direction, we're going to say it's coming from the Y direction and going to the X direction. So we're going to say tau YX is going to be equal to, and we have V, which is going to be negative 9 kilonewtons. We already found that out, multiplied by Q, which is that crazy number. I'm just going to simplify this to 1.0417, and that's going to be EE to the negative 5 divided by, that's going to be, so that's VQ divided by IT. So I is going to be 3.07 EE to the 1, 2, 3, 4, 5, 6, 7, negative 7, multiplied by the thickness, which is just 0.05 at that point. And I'll plug that into my calculator. That's going to be tau YX, which is equal to 9 times 1,000, right, because that's kilonewtons, times 1.047, whoops, 0.0417, equal to that, times 9 times 1,000, divided by 3. Oops. I keep messing up my calculator. Okay. Let's do this again. 4.1.0417 e to the 5 negative 5.07 e to the 7 negative divided by 0.05 times 9 times 1000. So that's going to give us this crazy number, 6107687. Whoops, that's supposed to be a 7. 7687. Yes, 0.296. And that's going to be in pascals. So I actually am going to triple check that because I feel like I've messed this up already. Alright, times 1.047 E. Okay. Okay, yeah, that's the correct. And to shorten this a little bit, since this is a crazy big number, we're going to push this over 6 decimal places. And we're going to say that our shear stress is going to be equal to 6.1 megapascals. All right. Well, that's the shear stress that is created at point H by reaction force at X. So we have like one done. And to really kind of hammer this through, we're going to make the stress blocks as seen by 3 different cut planes to really see exactly where this shear force is acting upon. And this will be important because we're going to need to combine all of these shear forces and shear stresses and normal stresses together at the end. So it's good to kind of create these stress blocks at each location when we find a new stress. So this stress block signifies point H. This is going to be our XY plane. This is going to be our XZ and XY plane. And we can say, okay, it's exclusively acting in the YX plane. Oh, this should be negative, by the way. This should be negative because this was a negative 9 kilonewtons. So because it's a negative 6.1 megapascals and it's acting specifically on the YX plane, we're going to go ahead and draw it like so, because you're going to have one shear force acting in the positive X, one shear force acting in the negative Y. You multiply those together, you're going to get a negative 6.1 megapascals. And it'll be drawn like that. And neither of these two cut planes will have anything. It's nothing. Okay, so that's one set done and done for our transverse shear force. Now let's go ahead and solve for our y. These will go faster as we kind of continue. So Ry, we can see where it's acting upon. It's acting in the longitudinal direction, and it is a force, so this is actually going to create an axial stress. Axial stress instead of a transverse shear stress. And the equation for our axial stress is just going to be the stress is going to be equal to the force divided by the area. So this is going to actually be pretty done and done here quickly. Let's go ahead and look at it from the YX direction, same as we did for our transverse shear. And we'll say, okay, this is the Y, this is the X. This is our pipe. This is point H. And all we have to do is say, okay, this is our reaction force. It's going straight up in the longitudinal direction, right? It's going up because it's positive, so that's going to be 80 kilonewtons. 80 kilonewton force right there. Okay, so this force is going to act equally in all points of the cylinder on the bottom, right? So that includes point H. So we don't have to do any trickery as we did with the transverse shear. It's just going to be super easy, done and done. Stress is equal to the force, which is going to be 80 kilonewtons, divided by the area of our cylinder here, which is just the circle, right? Their diameter is 0.05. So that's going to be equal to pi r, which is 0.025 squared. And that's just going to be your stress. I'll go ahead and plug that in. That's going to be 80 times 1,000, because that's kilonewtons, divided by pi, divided by 0.025 squared. And that's going to give you this lovely number, which is very large, but we'll shorten it later. 407,43665.43, and we'll shorten that, and we'll move the decimal place over 6 again, and so we'll say that's 40.74 megapascals. Watts and pascals. This is megapascals. So we say, okay, what direction is this operating in? As in, what is this force going to look like on our stress blocks? So we say, okay, here's your stress block of our relevant planes, x, y, z, z, x, y, and here's a little thing. And we say, okay, this is an axial stress. It's acting in the longitudinal direction. It's always pointing up in the y direction. Keep in mind, this is a compressive force because you have a lot of these downward forces that's kind of pushing our structure down. The reaction force is pushing up. This is going to be compressive, which means we are going to have to make this negative. If it were in tension, as if it was going down and kind of pulling the material apart, then it would be positive. So since this is compressive, we're going to have to make this negative, and it's compressive in specifically the y direction wherever it exists at. So we have a compressive force here at this y direction on this stress blocks, and a compressive force here on this y direction on this stress block. It's going to be signified by negative 47.74 megapascals. Negative 40.74 megapascals. Okay, and that's done and done. So we're actually through with figuring out where the stresses have been created by our reaction forces. So now let's go figure out where the stresses have been created by our reaction moments. So let's go ahead and let's label this mx here. We'll say, okay, mx. Now let's take a look at how mx is actually operating in this FBD. So mx is a moment. It's actually not acting in the longitudinal direction as my is. It's a moment acting in the lateral direction. So that means this is going to create a bending stress. Come down here. Bending stress. And the equation we're going to be using for that is my divided by I. So, and that's for your normal stress. Remember, sigma signifies a normal stress, as this guy does. This is normal stress. It's going, directly down. Your shear stress would have been, for a bending stress, is equal to VQ divided by IT. That is going to come to 0, and I'll tell you why in a second. And we're really just going to be worrying about our normal stress. But first, let's go ahead and draw from the view direction that the moment is not acting in. So we can see where this moment is acting in. Let's draw from the YZ plane. And YZ plane. That's going to be Y. That's going to be Z. This is our pipe, which again, since it's two-dimensional, is just a square. That's our pipe. Where's point H when we draw from this 2D view? That's going to be the very far left. So that's point H. I'll go ahead and double check that. Yeah, that's point H. And our moment is negative, and it's 32.5 kilonewton meters. Negative 32.5 kilonewton meters. It's acting along the x-axis. Negative 32.5 kilonewton meters. And since it's negative, it means that it's going clockwise. So it's actually going this way. And that's going to be our negative 32, negative 32.5 kilonewton meters. moment force here. Okay, so let's triple check because if this moment force here is going clockwise, oh yeah, I knew that looked kind of. For some reason, I knew I did that wrong. Yeah, so this is clockwise. That's counterclockwise. Okay. So I drew this going counterclockwise. This is clockwise. I'll go ahead and erase this arrow. And it's clockwise because it's negative. If it were positive, then it would be going counterclockwise. So now let's go ahead and discuss, at least firstly, why the shear stress is going to be equal to 0. Well, since we have this moment, our neutral axis is actually going to be coming along the x-axis right here. So if we go ahead and draw a circle here and kind of just like flip it up, we're kind of flipping it up. You know, we can say, hey, this is our z. This is actually going to be our x. Correct? And our moment is acting upon the z here, going kind of, it's kind of coming out of the page here, and it's going back into the page here, which means that our neutral axis is going to be here, and our point of interest is here. That's point H. And keep in mind, it's just kind of like a general rule that when your point of interest is at the outermost fiber, that your shear stress, when it's dictated by this equation, is going to be equal to 0. Why? Because our outer area is no area. The area that is on the left side of this point is no area. So Q is actually going to be 0, which means that we don't have to worry about this. So then all we have to do is worry about our normal stress. So let's go ahead and figure out, actually let's do this. M in this equation is just the moment. So that's just going to be the force of this moment. So that's just going to be 32.5 kilonewton meters. I'm leaving the negative out of that, and I'll explain why. Y here, that's just the distance from the center of your circle. Or sorry, from the center of, that's the distance from your neutral axis that your point of interest is at. So that's just going to go ahead and be your radius, since this is your neutral axis and this is the distance away from it is just going to be your radius. And I, again, is your moment of inertia, and that is going to go ahead and be dictated by the equation. Since this is a circle at the cut plane, 1/4 pi r to the 4th. Which I'll go ahead and solve that for that right now. Y to the 4th times pi divided by 4. That's, yeah, we already kind of knew this from a previous problem. It's going to be 3.07 e to the negative 7. So let's go ahead and plug each of these numbers into our original equation. We're going to have stress is equal to 32.5 kilonewton meters multiplied by 0.025 meters divided by 3, whoops, what was that? 3.07 e to the negative 7. And I'll plug that into my calculator. And that's going to go ahead and give us a normal stress of, we have 32.5 times 1,000, because that's kilonewton meters, times 0.025, divided by 3.07 e to the 7 negative. And that's going to give us a pretty big number. It's this monstrosity, 264,657,9805. Okay, and we're going to shorten this. 1, 2, 3, 4, 5, 6, 7, 8. I'm actually going to bring the decimal place over 9 places. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's give us 2.65. That's going to be gigapascals, since this is originally in pascals. So that's going to be our normal stress that is given to us by this bending stress from mx. Let's go ahead and create the stress blocks for this and figure out where exactly this is implemented on. So that's a stress block. That's a stress block. It's a process. Oops. And this is a normal stress. And we say, okay, well, where exactly is this normal stress acting on? Well, again, each of these stress blocks, it's a point. This is point H. This is point H. So it matters what is happening at point H. And what's happening at point H is that it is being compressed. So if this were going the other way around, let's say going this way, then it would be point H would be being pulled down, and that would be positive. But this is going to be being compressed, which is why I only solved just for the magnitude for this bending stress, so we can kind of give the sign depending on whether or not the arrow here, which in our diagram is compressing or pulling at specifically this moment. Again, if our point of interest were here, then this would be pulling, this would be in tension. So let's go ahead and say that this is going to be in compression. And it's specifically, again, in the y direction. It's going to be in the y direction. So at all points in the y direction, we have a compressive force. And that compressive force is going to be negative 2.65 gigapascals. Okay, so that's moment at x done and done. Let's go ahead and solve moment at y. So let's go and check out our FBD again and see what we can gain from this. The moment at y is actually acting in the longitudinal direction, meaning that this actually isn't going to be a bending stress that's created by our reaction moment at y. It's going to be a torsional stress. A torsional stress. Torsion stress. And the equation for torsional stress, specifically torsional shear stress, is going to, since if it's torsion, it means we're not getting normal stress off of this. Our torsional shear stress is just going to be equal to our torque times rho, which is our distance from the center of our circle or center of our geometry to wherever the point of interest is, and divided by our polar moment of inertia, which is slightly different from our moment of inertia. It's signified by a J instead of an I. And you can also look this up in your Mechanics of Materials book, which we'll get into in just a hot second. Let's go ahead and kind of draw this out. When we're looking at a torsional stress as in a moment that is being applied in the longitudinal direction, it's best just to draw the circle that it acts about. So we're just going to go ahead and find a bottom view of the circle. This is going to be in the XZ plane, XZ. So we'll say this is X, oops, X, this is Z, and this is our circle. This is just the bottom view. I know that's kind of a bad circle, but you can pretend that it's better than it is. Where's our point of interest on this? We'll check out our FBD again. That's just going to be directly on the outermost fiber of our circle on the Z. So that's going to be point H. Okay. And let's just plug stuff in. Though, keeping in mind, we have to draw our moment reaction force, right? Our moment is negative 22.5, which means, again, it's going to be going clockwise. And it's 22.5, right? 22.5 kilonewton meters. And it's going clockwise. So it's going clockwise, negative 22.5 kilonewton meters. Clockwise. All right. So tau is going to be equal to, what's torque here? Our torque is just our moment, so we'll just plug that in as is, negative 20. Actually, before I get into this, let's talk about where this shear stress is acting, what plane this shear stress is acting upon. So it is acting around this axis. This is the y-axis, right? It's just a dot. It's kind of coming out of the page or going into the page, whatever you think. So it's coming from the y-axis, so we say y there, and it's going to be pointing towards the direction that the point actually isn't on. So it's going to be directly towards x. So this is going to be on our xy plane. This shear stress is going to be acting upon our xy plane and no other plane. So And that's going to be equal to, first of all, we're going to see our torque. Our torque is just dictated by our moment, which is going to be negative 22.5 kilonewton meters. Rho is just the distance from the center to our point of interest, which is just going to be our radius of our circle. That's meters. Divided by our polar moment of inertia, which is just 1/2 pi polar moment of inertia for the circle. This is our cup plane, right? For the circle, which is going to be 0.025 to the fourth. Again, if you don't know, this is slightly different. If we're talking about our moment of inertia, this would be 1/4 pi r to the fourth. This is our polar moment of inertia, so this is 1/2 pi r to the fourth. It's a very slight difference. And again, you can look this up in the textbook. So let's go ahead and plug those numbers in, and we can solve that for our shear stress, which is tau yx, which is equal to 22.5 negative times 1,000, because that's kilonewton meters, times 0.025. Oops. Times 2 divided by pi divided by 0.025 4 times. I keep messing up. So that's going to give us this atrocity of a number, which is negative 916732472.2. And I actually am going to go ahead and move that over. 1, 2, 3, 4, 5, 6. That's 6 decimal places, so we'll say that tau yx is going to be equal to negative 916.73 megapascals. Okay. And we'll create our stress blocks for that as well. Again, we probably don't need to even really draw the planes for our xz and yz, because this shear stress isn't acting upon that plane. It's acting specifically upon the y-axis we talked about before. And this is going to be negative, so we'll draw that shear stress as such. It's going to be acting in this direction. That's going to go ahead and be a negative 916.73 megapascals of shear stress specifically on that block. Okay, cool. So we actually only have one more thing to solve for, which is our moment in the z. And as you see, that's going to actually be the easiest one, which is super cool. So moment of z, let's go ahead to the top and check out our free body diagram. This is going to go ahead and be a bending stress in the because it is a moment that is acting in the lateral direction. So this is going to be a bending stress. mz bending, which means we get to use the same equation that we used before, which is that our normal stress is going to be go ahead and equal to my. Our shear stress is going to go ahead and cancel out for the previous reasons that I mentioned before, so I'm not going to write it down. This is just our normal stress. This is what we're looking for. Let's go ahead and draw mz from the plane that it's actually not acting in. So this is, we'll draw it from the yx direction. Yx. Here's your pipe. And here's mz. And mz is positive, meaning that's actually going counterclockwise this time around, not clockwise. And h is in the dead center of our diagram. So h is going to be here. It's going to be going counterclockwise. And that's going to be like 61.5. I forget. What was the magnitude of our mz? Yeah, 61.5 kilonewton meters. Okay. So let's go ahead and draw. If we flip this up, once again, this is going to be our x. This is going to be actually our z direction. XZ. It's flipping this up this way. Yep. H is going to be right here. And this moment, as you can see, if it's acting, it's kind of coming out of the page here. It's coming out of the page here. It's going into the page here. Means our neutral axis is right there. So y is, again, what is y? It's the distance from the point of interest to the neutral axis. And as you can see, the point of interest is directly on our neutral axis in this case. So y is going to be 0, which means that our stress here is also going to be 0. So I'm actually not even going to draw the stress blocks for this one. We don't add anything. mz is just 0. So now that we have all of our stress blocks figured out, and we have each stress figured out, we're going to go ahead and combine all of the stress blocks that we have created thus far. So I'm going to say combined. Voltron assemble. Okay. Our stress block in the XY. Stress block here, here. Oops. So we're going to go through each of our stress blocks that we've already created and just kind of add them up. So first of all, I'm going to be looking at our XY, specifically shear stress in the XY. So we have 6.1 megapascals. I'll kind of put that into my calculator, specifically negative 6.1 e to the 6. 6.1 megapascals in shear stress in our XY. So if we go down, is there any other XY that has shear stress? No, 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 no. Ah, yes, we have also that shear stress in the XY. So I'm going to actually add those two together. So negative 6.1 megapascals plus negative 916, 9.163 e to the, for me, I'm going to do 8. Yeah. And I'm going to add those two together, which, unless there's, nope, that's it. So if our total shear stress on the XY plane is actually going to be equal to negative 9.2, oops, negative 922.83. And that's going to be megapascals. Okay. This kind of looks like a bad megapascal. I am actually going to rewrite that really quickly. Megapascals. Okay. So, what about XY? Our normal stresses. No normal stress here on the XY. There is a normal stress here, so that's going to be negative 40, 40.74, negative EE to the 6. So you have negative 40.74 normal stress in the XY plane. Anything else? Yes, we're going to have to add that to our, so add that to 2.65 negative EE to the 9. And we have to add those stresses together because they are going in the same direction. Anything else? Nope. Okay, which means we have another compressive force going in the y direction. That's going to be equal to negative 2.69 gigapascals. 2.69, because that is the combination of your 2.65 gigapascals plus your 40.74 megapascals. That makes sense, right? Yeah, that makes sense. Okay. So that's our stress block for XY. This is the torsional stress. This is the normal stress, right? So then let's go ahead and look at XZ. Is there's anything going on in XZ stress blocks? Nothing, 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 nothing. So we have nothing for XZ. What about ZY? Let's go the way up. Anything going in the ZY plane? Nothing. So we do have a negative 40.74 megapascal stress there. And that is going to be added on to a negative 2.65. We have actually already added those stresses together, so we know what the answer is going to be like that. So we'll go ahead and add a compressive force that's going to be identical to the compressive force that's existing here. That's going to be negative 2.69 gigapascals. All right. And that's it. That's all of our stresses combined at point H. And from here, now we can finally solve for the principal stresses and the max shear stress, which is what the original problem statement asked us to. We can go ahead and do that using our dope equations here. So we're going to say that our principal stresses, which is stress 1 slash stress 2, is going to be equal to. And we have to choose the stress block that's undergoing the most stress if we're looking for our max, shear stress slash, our principal stresses. That's obviously going to be XY here because this has a negative shear stress as well as the same normal stress that ZY does. So we're just going to be focusing on this stress block. It has the most stresses on it, which is fairly obvious. If it wasn't obvious, you could just solve for each stress block and see which one gives you the largest numbers. So we'll go ahead, and the equation for this is going to be equal to stress x minus stress y, plus stress y divided by 2 plus rad. We stress x minus, I got those mixed up, minus stress y divided by 2 squared plus, and then that's going to be tau xy squared. And we just got to plug numbers in. So let's go ahead and do that. Stress 1 slash stress 2 is going to be equal to, what's stress x? We don't have a normal stress in the x direction. That's 0. So it's going to be 0 plus negative, that's going to be 2.69 gigapascals. So I'm just going to actually say minus 2.69 gigapascals divided by 2 plus 0 minus a negative number is going to be 2 plus 2.69 gigapascals divided by 2 squared plus tau xy, which is just negative 922.83 megapascals squared. Okay. We'll kind of plug this into the calculator. Oh, this is plus or minus too. This is plus or minus. That's how you get 1 and 2. So 2.69 divided by 2 is going to go ahead and equal to a negative 1.345 gigapascals plus or minus. Now I'm just going to go ahead and plug all of this into the calculator. So I'm going to go ahead and say 0.92283 squared. Keep in mind that this is in megapascals. This is in megapascals and this is in gigapascals. So one's going to be to the 6th, one is going to be to the 9th. Squared 0.92283 squared plus 1.345 squared equal to that. Rad this into the calculator is going to be plus or minus 1.63, and that's going to be gigapascals. Okay, so this right here is our max shear stress. That kind of makes sense. If this were Moore's circle, this is just the radius of Moore's circle. So it's plus or minus, meaning it could go straight up or straight down. So I'm going to go ahead and just let you guys know this is our max shear stress. It's just whatever this term here turns out to be. As for our principal stresses, stress 1 is just going to be, we'll say 1.63, we'll say, okay, 1.345 negative, we'll say minus 1.63. That's going to give us our stress 1, which is going to be equal to negative 2.975 gigapascals. Stress 2 is going to be equal to 1.345 negative plus, we'll say plus this time, 1.63 gigapascals, which is going to be equal to actually a positive 0.285 gigapascals. And of course, our tau max is just 1.63 gigapascals. And there you go. Those are your principal stresses and your max shear stress. All right. That's it. That's how you solve the problem. So I'm going to end it off here. Yeah. Cool.